All right, good afternoon, everyone. We are very pleased to have Dr. Erin Mayfield, who is a postdoctorate researcher at Princeton University, join us to talk about the groundbreaking work that two groups at the university are doing in terms of helping us get that technical roadmap ready for net zero emissions by 2050 here in the US. And I'd like to start off by just doing a brief intro for Dr. Mayfield. She is an environmental engineer and public policy researcher with expertise in complex systems analysis, optimization, and environmental economics. In 2019, she completed her PhD in engineering and public policy at Carnegie Mellon. Congratulations, Erin. Researching the air quality, climate, and labor market impacts and equity implications of energy system transitions. She previously worked as an environmental consultant on natural resource damages litigation and ecosystem service modeling, and has held positions at the U.S. Environmental Protection Agency, the U.S. Congress, and the Environmental Law Institute. She received her bachelor's degree in environmental science from Rutgers University and earned her master's degree in environmental engineering from Johns Hopkins University. And with that, please help me welcome Dr. Mayfield. Thank you.
Thanks, Larry. Happy to be here. So today my presentation is about a multi-year study we conducted on transitioning the US energy system to net zero emissions by mid-century. The principal investigators of this project are Jesse Jenkins, Eric Larson, and Chris Grieg, and it's a collaboration with multiple researchers with expertise regarding different facets of the energy system transition. So there are several other studies out there that look at different techno-economic pathways to achieve net zero emissions. What our study is trying to do, in addition to modeling alternative techno-economic pathways, also doing more spatially resolved infrastructure planning, for example, where we cite solar, wind, and transmission infrastructure, more detailed analysis of investment needs. And also we explore impacts related to labor markets and air quality. So in this presentation, I'm going to kind of jump through at a high level different aspects of this study. It's worth noting that we did publish an interim report in mid-December. There's a lot of other studies that are coming from this that are going to work their way through the peer review literature. We're also going to host this site, which starting to add data at the end of January, which includes a lot of output from these modeling exercises. So kind of to start off, I wanted to go through kind of the different pathways that we modeled. So this is a look at primary energy supply, and you can see the 2020 primary energy supply, and then a snapshot in 2050 for a reference case. So that's effectively assuming no new policies, kind of business as usual, least cost scenario, and without any emissions constraint. Then we also model 5 different main net zero America pathways with differing assumptions regarding the rate of electrification, the availability of biomass, and the extent to which renewables can be deployed. In addition to these 5 main net zero scenarios that I'll focus on in this presentation, we modeled dozens of other scenarios with different assumptions regarding technologies and costs and other constraints related to technologies and deployment. So I'll walk through kind of these different 5 main net zero scenarios. So there's the E+ case, in which we assume there's a very high rate of electrification of vehicles and residential and commercial buildings. For example, we assume that half of all light duty vehicles sales by 2030 are electric and 100% of sales are electric by 2050. In the E+ scenario, we also assume that there's very few supply side constraints, with the exception of some land use change constraints. And we also do allow for underground CO2 storage. Moving to the E- scenario, we adopt essentially the same supply side assumptions as the E+ scenario, but we assume that electrification occurs less rapidly. In the E-B+ scenario, there's a higher degree of biomass available. And in the E+ RE-, we assume there's constraints on the deployment of renewables. And in the E+ RE+ case, we assume that by 2050, 100% of our primary energy supply is from renewable sources. So we wanted to kind of see kind of the range of different potential technological futures, and then move into the downscaling or the more highly resolved infrastructure planning aspects. So some of the key takeaways of this figure is that fossil fuel use is significantly reduced across all scenarios, with some residual use to account for some industrial and jet fuel in later years. Across all scenarios, there's a really high penetration of wind and solar. Bioenergy is also appears in all of these scenarios for its ability to be converted into carbon neutral negative fuels, and nuclear plays kind of a modest role in all of these scenarios. So these are some of the 6 key pillars that we identify that are consistent across all of the scenarios. And I'll give some more details regarding each of these pillars in future slides. So end-use energy efficiency and electrification, much the rapid. We rely on clean electricity, both including wind and solar generation and transmission, but also firm power resources. Bioenergy and other zero carbon fuel and feedstocks also play a role. CO2 capture, utilization, and storage plays a role to some extent in each of the scenarios. This relies on reduced non-CO2 emissions such as methane, as well as enhanced land sinks. So in this figure, we show that the annual generation by different resource, and you can see clearly that solar and wind play a large role in all of these scenarios. So solar is represented by kind of the yellow shaded area. Offshore and onshore wind is represented by this green and blue area, and you can see kind of it plays a large role in all the scenarios, kind of bounded by kind of our renewables constraint scenario here to our high renewables scenario, where 100% of primary energy supply comes from renewable sources. So solar and wind grow to about 50% of all electricity by 2030, up from 10% today, and by 2050, 80 to 90% for 3 of the 5 pathways comprise renewables. So even when renewables are heavily constrained, upwards of 45% of electricity is supplied by renewables by 2050. And so, as I said, we did our kind of the more typical techno-economic pathways modeling using supply side optimization. In addition, we did a lot of more spatially resolved planning modeling, so where you would actually site this infrastructure. So with respect to solar, wind, and transmission build-outs, we modeled where infrastructure can be sited given different environmental and cultural land use constraints. So this is a snapshot in 2020 of the current solar, wind, and transmission infrastructure. So everywhere in blue is where we have existing wind infrastructure. everywhere in brown, which is a little bit hard to see here, which is utility scale solar. And all the gray lines is transmission infrastructure. So in 2019, there were about 100 gigawatts of wind and 35 gigawatts of utility scale solar. 2020 may have been a record-setting year with about 40 gigawatts of wind or solar added, which is about the pace needed at the very start of the transition, but that must rapidly accelerate over time. So this is a snapshot for our E+ scenario in 2050 and what the solar, wind, and transmission build out may look like. So by 2030, about 600 gigawatts of new wind and solar are deployed, and transmission expands by about 60% from current levels. And by 2050, there are about 1.5 terawatts or 1.5 million megawatts each of wind and solar. And by 2015, transmission nearly doubles. So moving on to bioenergy, this is another snapshot of 2050 and what the build out may look like for an E+ scenario. And we estimate that about $700 billion in capital must be invested across rural America by 2050, basically creating an entirely new bioenergy system. So this entails more than 1,000 new bioenergy conversion plants that produce hydrogen, synthetic fuels, petrochemical feedstocks, and electricity. Bioenergy accounts for nearly 1/5 of primary energy by 2050, which can be used to produce carbon neutral liquid and gas fuels, or produce hydrogen via gasification, and to capture CO2 and store it underground. So, and if biomass is constrained, then we would need some alternative source, such as direct air capture. So skip to this. We also look at what the expansion or the creation of a CO2 transport and storage network would look like. So in this figure, all the areas in shaded areas in gray, that's where potential injection basins are located. All of the dots represent different CO2 point sources or infrastructure. So all the green areas is the biomass facilities. Blue is where you have industrial facilities, and orange is where you have natural gas plants with CCS. And we cite all of these sources proximate to and through an iterative process with transport and storage network. So we cite all the trunk lines along existing natural gas corridors, and then cite additional distribution lines as well. And so this is just kind of an example of a potential future CO2 transport network. And this amounts to a capital investment on the order of $200 billion. So I walk through kind of the higher level techno-economic optimization results, some of our downscaling efforts, and now I'll go at a high level some of the impacts that we modeled, including employment and air quality. So here we show the supply side energy jobs over time across the different scenario. So I think it's important to note here that we're not modeling our demand side energy jobs. And for context, currently about 40% of total energy related jobs are in energy efficiency. So that's an important aspect of this, which we don't include in this analysis. So we focus on energy related jobs across supply chains, including coal, natural gas, oil, solar, wind, CO2, biomass, nuclear, and the electric grid. So we show that there's an average annual of about 3 million supply side energy jobs supported over the first decade in the net zero scenarios, which represents a net increase of about 500,000 to 1 million jobs over that decade. So a lot of these employment pathways are heavily influenced by technology selection, the rate of electrification, the extent of renewable deployment, and also changes in labor productivity over time. And you can see kind of the two bounding scenarios with respect to the net zero scenarios are related to the extent of renewables deployment here, where renewables is constrained in the E plus RE minus case, and where you have 100% renewables by 2050 in the E plus RE plus case. So we also show that there's a net loss in jobs in the fossil fuel sector in both the near and long terms, which is more than offset in aggregate by increases in low carbon sectors. So in this figure, we show net employment for the low carbon scenarios or net zero scenarios relative to the reference case scenario. So, and the distribution of jobs by resource sector. So every bar that's above the zero line, it equates to a net job gain in those resource sectors, and everything below the zero line represent a net job loss. So you see losses in oil, natural gas, and coal. So we also use our downscaling results to model the spatial distribution of jobs in the future. And so this is a snapshot for the E plus scenario. There's a lot of different assumptions that go into this. So in addition to the downscaling work that I showed, we modeled fossil fuel supply chains from extraction to generation and other sorts of end use. We also modeled the spatial distribution of things like solar and wind manufacturing. So there's a lot of embedded assumptions regarding the spatial distribution of this type of infrastructure and the resulting job outcomes and spatial distribution of those jobs. So we show in this kind of instantiation of the future for the E plus scenario, most states see a net growth in energy related employment, but there's going to be major shifts in local economies that need to be managed over time. This shows the percentage of the total labor force for each state that is currently employed and in the future could be employed in supply side energy related jobs. And so for most states, supply side energy jobs are as a percentage of the labor force increase in this future. And this is again for just the E plus scenario. We see kind of in some states that have a large fossil fuel industry like Wyoming and North Dakota, where you have 16 and 12% of the current labor force in supply side energy related jobs, and most of which are in fossil fuel sectors. You see some level of decline in those states. In other states that have almost kind of a very low percentage of their total labor force is employed in energy related jobs, for example, in Nebraska, where about 2% are employed now, given kind of the future resources, both in terms of biomass, wind availability, there's upwards of 16% of the total labor force may be employed in supply side energy related jobs by 2050. So these energy transitions can truly transform some of the state level economies. So in addition to labor impacts, we looked at air quality impacts. Here we're showing just the results related to exposure to fine particulate matter related to the emissions of PM 2.5, NOx, SO2, and VOCs. And here I'm only showing air quality impacts related to coal and natural gas, electric power generation, and the transition of the transportation sector. And we're currently modeling other sectors, including different industrial sectors currently. In addition, we focus on premature mortalities associated with exposure to fine particulate matter. And we're also currently modeling additional health outcomes as well. So we show that in the 2020s, most of the air quality benefit is associated with the rapid retirement of coal power generation. And then by the 2030s and 2040s, a lot of the benefit is related to transition of the transportation sector, although there's a large variation across the different scenarios, which is in part driven by the rate of electrification. So so I should point out that avoided mortalities are in terms of the net benefit of these net zero scenarios relative to our reference case scenario. So in aggregate, we see that there's about 200,000 to 300,000 premature mortalities are avoided across the different scenarios over this 30-year period, which equates to about $2 trillion to $3 trillion in air quality damage avoided from transitioning to a net zero energy system. So to give you kind of an idea of the level of modeling we're doing, those were kind of aggregate estimates across the US of air quality benefits. This is an example of our more spatially resolved modeling of mortality and mortality risks with respect to transportation emissions. And so you can see mortality risk in terms of deaths per 100,000 people at the county level in our reference case and our two different demand scenarios in 2020 and how it evolves over the time. So you can see clearly that the reference case, there's actually a slight increase in mortality risk for different localities. In the E- case, you see a decline over time. In the E+ case, by 2050, the mortality risk is near zero related to transportation emissions. So I reviewed kind of the techno-economic modeling, the downscaled infrastructure planning modeling, and some of the impact modeling work that we did, kind of to give you, moved kind of to the bigger picture and the major takeaways from our efforts. I'll go through a few slides related to kind of the aggregate portrait of this transition. So this transition is big, but it's affordable. And this figure shows the share of GDP spent on energy system costs over time. So starting in 2070 through 2020, you can see the historical energy system cost as a percentage of GDP. There's a lot of variability over time. And you can see spikes because of oil price shocks in the global financial crisis of the late 2000s. And then you see the future scenarios. You see the reference case and the different low carbon cases. So in these different low carbon cases, the share of GDP spent on energy is below historical levels across all the low carbon scenarios. And of course, our modeling is on some level assuming perfect foresight. It's assuming coordination between different parts of the energy system and ability to mobilize in capital investment. So another analysis was done that more specifically looked at the capital investment needed and the timing of that investment, because of course it's not going to be overnight. There's going to be some lead time of that investment to mobilize it. So this shows over the first decade that about $262.6 trillion has to be committed to supply side plant and infrastructure in the 2020s. So this is about a two times increase relative to the business as usual case. So modeling all these scenarios, we wanted to understand what the priorities would need to be in the 2020s and consistent across all of these scenarios, despite kind of variation in future years with respect to how these transitions could occur. So there's kind of 8 main priorities for the 2020s: build societal commitment, investment, environment, and delivery capabilities, improve end-use energy productivity and efficiency, electrify demand, including buildings and transportation, decarbonize and expand electricity, prepare for major expansion and transformation of the bioenergy industry, build a lot of infrastructure, and enhance land sinks and reduce non-CO2 emissions, and innovate as well, our technology toolbox. Kind of to give an aggregate portrait of the blueprint for the next decade, we need about $2.5 trillion in additional investment. So this is additional investment in the net zero pathways versus the reference scenario. So you'll see the areas in blue, about 50% or $1.3 trillion of the investment is in wind, solar, electricity transmission, and other network infrastructure. And you'll see the areas in brown and dark green, which represent about $0.7 trillion, or about 30% of the investments is on the consumer side related to vehicles, buildings, and appliances. And the area in yellow, which is about 0.4 trillion, or 15%, is in the industrial sector, mostly for process efficiency improvements. And so this is all in the first decade. You'll see the smaller orange box down here. There is some divergence in the different scenarios, and we would need about $100 billion in what we're calling option creation, which can help mitigate different transition risks by preparing for different potential futures. I'll go over a few kind of more detailed elements of the 2020 priorities, with just a focus on the things that may be more relevant to this audience. So I'm going to skip through most of this and just kind of look at some of the things related to buildings and energy efficiency. So with respect to improving end-use productivity and efficiency, we need to reduce building space conditioning, energy use through improved building shells, electric heat pumps, and controls, ensure the adoption of the most efficient end-use appliances and consumer devices. With respect to electrification of buildings, we need to deploy heat pumps in 1/4 of current residences by 2030. So that's 25 to 30 million households, plus 15% of commercial buildings, and focus on new builds and end-of-life replacement of the current stock. We would need to deploy electric heat pump residential water heaters as end-of-life replacements for existing units. And one more element I'll point out is related to the expansion of electric distribution infrastructure. So we need to strengthen the distribution system planning, investment, and operations to allow for greater use of flexible demand and distributed energy resources, improve distribution network asset utilization, and efficiently accommodate a 5 to 10% increase in peak electricity demand from EVs, heat pumps, and other new loads by 2030, and also be preparing for a more rapid electrification and peak demand growth after 2030. So again, I'll skip through these other pieces of the transition. And with that, I'm happy to take questions. And again, this was a large team that worked on this. My expertise is in the fossil fuel transitions, as well as modeling labor and air quality impacts. So I'll answer all questions to the extent that I can, and I'll also refer you to other researchers on our team or other resources where we post details regarding this modeling to better help answer some of the questions you may have. Thanks.
Thank you so much, Erin. Yes, we have quite a few questions in the queue, and we'll try to get to as many of them as we can. There were a few related to CO2 capture and storage. And one question was, how far along are we in terms of that technology? And then alongside that, is the proposed CO2 storage to be located at discarded oil and natural gas drilling sites? And what's the possibility for contamination? Or should I say, what is the possibility of creating hydrogen sulfide gas as the CO2 combines with the remnants of fracking acids?
Okay, so the lead of the work on modeling CO2 capture, storage, and utilization was Chris Grieg, and I can kind of speak a little bit to some of the efforts there. So across all of our scenarios, we're assuming that the technology has to be proven to the extent that there are pilot projects, but not necessarily at scale. So a lot of these technologies have to be further proven and to be able to deploy at scale. That's without question. And that's not just true of our CO2 networks. So this requires some level of innovation. With respect to CO2 storage, there's some overlap between where you have potential injection basins as well as where you have historical upstream oil and natural gas extraction. To the extent of making assumptions regarding that the injection is actually occurring in at existing upstream fossil fuel sites, we're not making any assumptions regarding that. We have kind of at a state level what the injection may look like, but the really injection fields have to be further explored to really understand kind of the potential going forward, and also the costs, and also where networks would be, and all of that. There's a lot of uncertainties related to that. With respect to potential environmental contamination, we didn't explore that with respect to CO2 storage and injection, but of course it should be a concern and upfront. And this has been kind of a historical and repeated issue with fossil fuel development that will have to be addressed without question in our planning and processes.
Then it's certainly a consideration that extra level of innovation will perhaps add then to the cost of these various scenarios, or has that cost of innovation been somewhat modeled into this too?
So with respect to costs, we're largely in our base case, and we do a lot of sensitivities related to costs. In our base case, we're using NREL's mid-range ATB cost assumptions over time for most of the technologies. So it relies on declining costs of all of these technologies, including solar and wind. And so there's some level of innovation, increasing productivity related to labor, and many other additional factors that go into declining costs for all of these technologies. So embedded are assumptions of kind of innovation for these technologies.
Another question regards thermal energy storage, whether via solar hot water heating or ice storage. right? Were those also considered in the modeling of these scenarios?
So that is not my expertise. That you can refer to, we have kind of detailed technical annexes posted on the website for this report, which walks through the assumptions regarding thermal energy storage.
Okay. All right. And given also the way that biofuels play into these scenarios, what is the potential impact on land use and food production relative to biofuel generation?
Mm-hmm. So in all of our net zero scenarios, except the one which was called E minus B plus, we're assuming that kind of there's no net land use change with respect to, so it's not impacting kind of resources, food, agricultural lands. And we assume kind of there's the same biomass potential as current rates. In the E minus B plus case, we assume that there's an enhanced biomass resource. And so this work was done by a few different researchers, like the downscaling biomass work was done by E.J. Baik at Stanford. And then we had a group of researchers at Colorado State that focused on the land sink. And again, there's detailed annexes related to that work.
Okay. Next question from one of the college faculty in the BEST network, who's very complimentary of the work that's been done so far. Two questions regarding the mortality index modeling. Did you use the air quality index, and can your model be easily applied to a place like India? So we'll start off with that.
Okay, so the modeling results that I'm showing here, I used the what's called the AP3 model. So I built an emissions model, which and using this reduced complexity air quality model that is specific for the US to develop spatially resolved estimates of impacts. We're also using in parallel, because there's uncertainty in the reduced complexity models and the chemical transport models, two additional models to better validate or present our level of uncertainty with respect to the air quality impacts, especially over the long term where you have potentially changing air chemistry. So this model is really, or these models, that suite of models that we're using are really specific to the US. But analogous approaches, given the availability or noting the constrained availability of data for India, we can't use the same model, the same suite of models, but there's certainly experts that do model India air quality, including, for example, Denise Mazeroll at Princeton.
All right. Let's see. Well, the second part's already been covered by a previous question. And then what about building envelope improvements, and also kind of looking at kind of the balance between renewable energy and energy efficiency, right? How do they compare throughout these scenarios?
Yeah, so with respect to kind of demand side assumptions, we have kind of three main scenarios. Our reference case, our E plus case, which is high rate of electrification, and our E- case, which is still a high rate of electrification, but not quite as high. All of those assumptions are, again, within an annex based on modeling done by Evolved Energy research, and so you can kind of see kind of demand sector by sector what the assumptions are over time. So kind of there's three main demand scenarios essentially that we're modeling, and I would say they're not optimized. So on the supply side, we're trying to optimize and minimize costs. On the demand side, these are just set assumptions that feed into our supply side optimization.
Thank you. Unfortunately, we are at the close of our session. There are a few other questions that I hope I can send your way for follow-up, and then we can take those answers and share them via email. So that's what I'd like to propose doing. There were just a ton of really interesting questions. This is, as you might imagine, a very complex study. And we had hoped to include this December report in our resources booth, but it's a rather large file. So what we've done instead is to include the link. If you look at the auditorium program, right, there should be a link under Erin's session that'll take you to a page. And in fact, you can download that December report if you go towards the almost the bottom of the page. So with that, thank you so much. A lot of great work.